All right, we are back and we're picking up from where we left off. So, origin of the solar system. Okay,
Yeah.
and so our sun is thought to have formed when gravitational attraction pulled together swirling clouds of hydrogen gas and dust called nebulae in a region of space where their density was high. Right, meaning there was more of them per unit volume. That's what density is, mass per unit volume. The solar system may well have been formed at the same time, about 4,500 million years ago, with the planets being created from the disk of matter left over from the nebula that formed the sun. Right, so the sun was formed, and whatever is left over for made, was used to make the planets. Again, right? I believe this. Yeah. So they use the word may. So right, not sure if that's exactly what happened. As this material rotated around the sun, the gravitational attraction between the small particles caused them to join together and grow in size in an accretion process. Right, so accretion process like coming together and growing. A rotating accretion disk is thought to have formed from which the planets emerged. Evidence for this accretion model of the formation of the solar system is the approximate age of the Earth, which has been found by the radioactive dating of mineral rocks. So we've done radioactivity, and so rocks can be identified from the radiation that they emit. And so using that, right, we have come to know, right, further information was provided by the rocks brought back from the moon, found to be about 4,500 million years ago. Right, so putting all that together, we get like, okay, maybe the Earth is just as old as the sun or something, right? And the way it came together. The view that the whole solar system was formed at the same time from a rotating disk of accreting material is also supported by the fact that the orbits of the planets are more or less in the same plane and all revolve around the sun in the same direction. Right? So it's not like one's going clockwise and the other is going counterclockwise. They're all moving counterclockwise. Neither of these circumstances are likely to have happened by chance. Okay?
Yeah.
To account for the existence of heavier chemical elements in the sun and inner planets, it is thought that these might have come from an exploding supernova. During the lifetime of a star, atoms of hydrogen, helium, and other light elements are fused into atoms of heavier elements. It is likely that matter from previous stellar explosions mixed with interstellar hydrogen before our sun and the planets were formed, making our sun a second generation star. So something happened before our sun was formed. Evidence for the presence of many elements in interstellar clouds of gas and dust comes from the visible light spectra. As the sun grew in size, it became hotter. In the region of space where the inner planets were forming, the temperature would have been too high for light molecules such as hydrogen, helium, water, and methane to exist in a solid state. As a result, the inner planets are built from materials with high melting temperatures such as metals and silicates. Silicates meaning what we call like compounds of silicon, so dust and rock and stuff. Okay. Small nodules
Yeah.
collided with each other to form larger bodies, and the planets began to grow. So it's like adding on, right? Clumping together. Since less than 1% of a nebula is composed of heavy elements, this means that Venus, Mercury, the Earth, and Mars only grew to a small size and are solid and rocky. So they're saying that's why. I mean, we can say like if it's only 1% and that was used to make 4 planets, then that nebula was like super huge, right? And that's the reason why the planets are all small, because there wasn't a lot of material to build them. Okay.
Yeah.
Further away from the sun, in the cooler regions of the solar system, light molecules could exist in solid icy form. Right? So we know that water is there. We have water as a liquid, hydrogen, helium are gases, methane is a gas, and that is because the temperature that we are at, because of the distance we are from the sun, and as well as Mars, Venus, and Mercury. Right? These guys cannot be solids. Further away, they can be solids. Right? Because it's colder there. So, right, the light molecules could exist in a solid icy form, being more abundant than the heavy elements. The outer planets could grow to a size large enough to capture even the lightest element, hydrogen. Right, so that's why these planets are much larger than Earth, and they are less dense because they don't have as much solids in them. So the outer planets Jupiter, Saturn, Uranus, and Neptune are large, gaseous, and cold. Together, their mass constitutes 99% of the mass orbiting the sun. So these 4 planets, right, have a mass that's 99% of the mass that's orbiting the sun. So, right, obviously
Yeah.
Pluto, the asteroids, the comets, the moons, and the 4 planets, Mercury, Venus, Earth, Mars, together are only like 1% of the mass of that's in the solar system. Like not in the solar system, but that's orbiting the sun.
Oh, okay.
That's
Yeah.
orbiting the sun, right? Because the
Yeah.
majority of the mass of the solar system, if you talk about the solar system, then the majority of the mass of the solar system is in the sun itself, right? So more than 99% of the total mass, more than 99% of the total mass of the solar system itself is concentrated in the sun, right? So what we're talking about is the mass that is orbiting the sun. So obviously there's a difference between the mass of the solar system and the mass orbiting the sun. So those are two different things. Don't confuse them. For the solar system itself, more than 99% of the mass is the sun itself. And that is why it has like a very high gravitational attraction. And that is why it's able to keep all these planets and satellites and asteroids and comets and everything in orbit. Okay?
Okay.
The gravitational field strength of a planet. Newton proposed that all objects in the universe having mass attract each other with a force called gravity. The greater the mass of an object and the smaller their distance apart, the greater the force. Halving the distance quadruples the force, right? So there's an inverse relation to the square of the force. The distance and the force is are inversely related, and the distance is inversely related to the square of the force. So halving it quadruples the force. For
Yeah.
a planet, the gravitational field strength at its surface depends on its mass, and it is nearly uniform across its surface. So that's why, you know, we have 9.8 meter per second square, which is the gravitational field strength, acceleration due to gravity, and also the gravitational field strength of the Earth. And it's roughly the same everywhere, right? There are like slight differences depending on on your position relative to sea level. So it's going to be somewhat less when you're like high up in a mountain, or down like at the sea or whatever, but more or less the same at the surface. The
Yeah.
strength of the gravitational field decreases as the distance from the planet increases. So the further away you are, the lesser the gravitational effect.
Okay.
Travel times. The planets and their moons are visible from the Earth only because they reflect light from the Sun. The outer region of the solar system are over 5,000 million kilometers from the Sun, and even light takes time to travel to such a distance. And as fast as light is, right, it takes time for it to reach those outer regions.
Yeah.
Right, so technically the position of the planet that we are seeing, like I just mentioned in the last session, right, that we
Yeah.
are seeing the planets, so that's probably not where they are when we are seeing them, because the light travels to them and then is reflected back and then we see it, and so it takes a lot of time for that to happen. And so in real time where they are is different from what we are observing them to be.
Yeah.
Right, similarly for stars, the stars are so
Exactly.
far away that we're only observing the light that has traveled like so long from so far away, and so that's not where the star is. And it's also like maybe theoretically possible that a star we are seeing in the sky, that we'll see in the sky tonight, is no longer there,
Yeah.
right? But it's just that the light took so long to travel that we're only seeing it right now, whereas in real time it's something's changed.
Yeah. Okay.
Okay, now here's a work example. Calculate the time for light from the sun to reach the earth. Right, so average speed is total distance over time, total time is total distance over speed. Right, so we know the speed of light is 3 into 10 to the power 8 meter per second. Right, what is the distance of the earth from the sun? That is 1.5 into 10 to the power 11 meters. So you do the math and you get 500 seconds, which is about 8 minutes.
Yeah. Okay.
Right, so this is
Yeah.
the part I said I'll leave to you to read. So you can read through this. This is just a lot of information. Right,
Yeah.
I'll just read this last part. So gravity and planetary motion. In topic 1.5, we saw that to keep a body moving in a circular path requires a centripetal force acting towards the center of the circle. In the case of planets orbiting the sun in near circular paths, it is the force of gravity between the sun and the planet that provides the necessary centripetal force. The strength of the sun's gravitational field decreases with distance, so the further a planet is away from the sun, the weaker the centripetal force. This results in a lower orbital speed, so the planets that are further away from the sun are moving slower, and that means they're taking longer to travel around the sun, to circle the sun. In the case of a comet with a large elliptical orbit, its speed increases as it approaches the sun and decreases as it moves further away. Energy is conserved with some of the kinetic energy it has when close to the sun being transferred into potential energy as it moves away. So they're bringing together concepts from energy and motion and stuff like that, right?
Yeah.
The moon is kept in a circular orbit around the earth by the force of gravity between it and the earth. Okay,
Okay. Yes.
so we're done with half of that. And now the very last topic.
Which we will do in next class.
Well, we are continuing now.
You said we will do it tomorrow.
Well,
Okay. 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 Yeah. Let's go.
yeah, that conversation we had before the start of class.
Yeah. I forgot.
Yeah. So, the sun as a star. The sun is a medium sized, so our sun is like medium sized, which consists mainly of hydrogen and helium. The radiant energy it emits is mostly in the infrared, visible, and ultraviolet regions. So, heat visible light, and UV, right? These regions are the electromagnetic spectrum. This radiation is emitted from glowing hydrogen, which is heated by the energy released in nuclear reactions within the sun. Remember, we know that in the sun, what's happening is nuclear fusion. Okay?
Yeah.
Nuclear reactions in stars. Stars are powered by nuclear reactions. Stable stars such as our sun are hot and dense enough in their center or core for nuclear fusion to occur, right? Nuclear fusion of hydrogen into helium. The high temperature in the core required to sustain the nuclear reactions is maintained by the large amounts of energy released in the fusion process. The sun is powered by nuclear fusion. So they basically said the same thing 3 times. Some of the energy generated in the core is transferred to the outer layers of the star, meaning the sun. These are cooler and less dense than the core, and like cooler comparatively cooler, right? Not like you can, freeze ice over there, but are still hot enough for the hydrogen gas to glow and emit electromagnetic radiation into space. Stars vary in age, size, mass, surface temperature, color, and brightness. Color and brightness both depend on the surface temperature, right? So they're white, blue, red. Ours is yellow, right? So color and brightness both depend on the surface temperature, which in turn increases with the mass of the star. So the larger the star is, the greater the surface temperature. Stars that are white or blue are hotter and brighter, so their surface temperature can be between 6,000 to 25,000 degrees centigrade. Then those that are red and or yellow, which have a surface temperature of 3,000 to 6,000 degrees centigrade. Not exactly cool, but compared to the other guys, yes.
Okay.
Then we're going to talk about stars. You see, that was short, wasn't it? This is short,
Yeah. Yeah.
right? We'll get through this in no time, hopefully.
Sure.
maybe I'll leave like a smidgen for tomorrow.
I highly doubt that. Okay, let's go.
Just a sec. I'm sort of planning my move. Okay, so we've got the universe, the Big Bang Theory, age of the universe, and so yeah, I think I'll just leave. Yeah, so I mean, yeah, let's do some of this. So the stars. The sun is our closest star and is so bright that it banishes the darkness of space with its light. It's like a fictional, dramatic line over there. It banishes the darkness. When the sun sets, due to the rotation of the earth, the night sky is revealed. The night sky is you basically facing space, right? Away from light produced by humans, the night sky presents a magnificent sight with millions of visible stars, something that we don't normally get to see, right? It looks like that, and that is something that I want to experience. Unfortunately, in major cities, it's not something you can experience, right? The image 6.2.1a. Anyway, coming back. So the night sky has been object of wonder and study since the earliest times. On a practical level, it provided our ancestors with a calendar, a clock, and a compass. On a theoretical level, it raised questions about the origin and nature of the universe and its future. In the last 100 years or so, technological advances have enabled much progress to be made in finding the answer and making sense of what we see. So you can see over here, this is also just like a lot of talk. Are you there?
Yeah, I'm
Yeah,
listening.
okay. I thought I was talking to myself. Okay. Although the stars may seem close on a dark night, in fact, the distances involved are enormous compared to the distance across our solar system. So great are the distances that we need a new unit of length, which is called the light year. Now, the light year sounds like, because it says year, we think it's a unit of time. It is not a unit of time, it is a unit of distance. What is it? It is the distance traveled by light in the vacuum of space within 1 year, right? And so what you do is you have the speed of light, which is 3.8, 3 into 10 to the power 8 meter per second. So it's per second, and so you calculate, oh, so if it's traveling that much in 1 second, how much is it going to travel in 1 year? And so you calculate how many seconds there are in a year. So how many seconds are there in a year? Hmm?
Are you asking?
Yes. So you've got 60 seconds in a minute, and 60
Yeah.
minutes in an hour, and then 24 hours per day, and then, right, 365 days a year. So that's 31,536,000 seconds a year. And you multiply that by 3 and 8 zeros. So
Oh,
that's 300 million, right?
wow.
And so what
Yeah.
I'm getting is like one, two, three. So that's billion, trillion, whatever comes after that. So that's 94608 followed by 9 and 10, 11 zeros. So 94608 followed by 11 zeros. That's a lot, right?
Yeah.
And
Yeah.
so as you can see in the yellow box over here, 1 light year is the distance traveled in space by light in 1 year, and it equals to nearly 10 million kilometers. 10 million kilometers, right? So 9.5 into 10 to the power 12 kilometers, or 9.5 into 10 to the power 15 meters, which is the SI unit.
Yeah.
So the star
Okay.
nearest to the solar system is Alpha Centauri. It is 4.31 light years away. So this multiplied by 4.31, and that is the nearest star to our solar system.
Oh,
That means
I see.
light traveling from it at the Earth today left 4.3 years ago. Right? So that's the nearest star. So if you're seeing it in the night sky, that light is like 4.3 years old.
Oh, okay.
Cool, isn't it?
Yeah.
So the pole star is 142 light years away, and so if you're seeing that in the night sky, you're like, oh, there it is. Like, no, that's where it was 142 years ago.
Yeah.
The whole of the night sky we see is past history, and we will have to wait a long time to find out what was happening there right now, right? So if we look at the right Alpha Centauri tonight, and then we wait for 4.31 years, and then we look at it again after exactly 4.31 years, and then we say, oh, so that's what was happening, that's where it was on the 25th of Feb 2026,
Yeah.
right?
Yeah.
Right, galaxies. A galaxy is a large collection of stars. There are billions of stars in a galaxy. As well as containing stars, galaxies consist of clouds of gas, mostly hydrogen and dust. They move in space, many rotating as spiral disks like huge Catherine wheels with a dense central bulge. the Milky Way, the spiral galaxy to which our solar system belongs. So our solar system is part of the galaxy that we have named the Milky Way.
Yeah.
Okay,
Okay.
can be seen on dark nights as a narrow band of light spread across the sky. So this, right? So we are able to see the galaxy we are in. And the reason why it appears as a narrow band is because we are in that circle. So when what do you see when you know lay a circle flat? You only see the thin circumference,
Yeah.
right? So that is what you're seeing.
Yeah.
So you've got some
Interesting.
definitions over there: the light year, the galaxy, the Milky Way, right?
Yeah.
We are near to the outer edge of the galaxy. So what we see when we look at the Milky Way is the galaxy's central bulge. Figure
Okay.
6.2.1b is an infrared photograph of the galaxy taken from beyond the Earth's atmosphere, clearly showing the central bulge. So you can see that is the central bulge, and
Yeah.
right, infrared. So that's the heat coming from the Milky Way, the galaxy we are in. That's a lot of heat.
Yeah.
And remember, white is hotter.
So there are
There's more heat
different
in the
types.
center. There's also like white spots as you can see somewhere out here, and so those are like
Yeah.
stars and whatever, and so it's much hotter at the center of the galaxy. We are at the outer edge, so somewhere over here, right, with the yellow star.
Yeah. Yeah.
Galaxies vary considerably in size and the number of stars they have, right? So some galaxies are larger than others. The diameter of a typical galaxy is 30,000 light years, not kilometers. 30,000 light years,
That's a lot.
right? So I mean, a human cannot even, like, even if you're traveling at the speed of light, which according to Einstein is like not possible because our mass will go to infinity, etc., right? Even if we think about that, it will take 30,000 years for us to, well, we are at the edge, right? So it might not take that long, but right, however long it's going to take, we're not going to survive it in terms of our lifespan,
Yeah.
right? So we're stuck on Earth.
Yeah.
We're stuck in our solar system. Right, galaxies travel in groups. That's interesting. So galaxies,
There are different groups.
I mean, the first thing that they're traveling, and the second thing that they're traveling in groups.
Yeah.
The nearest spiral in our local cluster is the Andromeda galaxy. I don't know if you've heard of it, right?
No.
So the nearest galaxy, the neighboring galaxy to ours has been named Andromeda. Like it's not its own name. It's not going to come in like, oh, hello, I'm Andromeda. We named it Andromeda.
Does it have its own planets?
Possibly.
Okay.
It is around 2.5 million light years away, right?
And how is it visible to the naked eye?
Because of all the stars and stuff. It's like the galaxy. You can't see it this way as you see in the image over here. You can see it like a dot,
Yeah.
a bright dot in the sky. So you're like, oh, that's Andromeda.
There's so many dots in with the lights. How would you know which one's which?
I mean, I'm pretty sure they have ways of figuring that out.
Yeah.
Okay,
Okay.
so origin of the star, life cycle of the star. So stars and the universe I'm going to leave for tomorrow, right?
Yeah.
And yeah, so tomorrow we will inshallah have this all wrapped up. Okay.
Yeah.
but do be on time. Okay, 3:30.
Yeah. Yes.
All right. I'll see you tomorrow then, inshallah.
Okay, and I would like to talk to you